Greg Erickson. I'm a co-founder of General Graphene Corporation, and I currently serve as its Chief Operating Officer. Although, in all candor, we're not that big on titles here at General Graphene. I'm going to talk to you today about electromagnetic interference, or EMI shielding. It's a topic about which not that long ago I didn't know very much, but I've since read 73 articles about it, and I'm going to tell you what little I know. EMI is nothing more than radio waves, and the radio waves are constantly bouncing around our environment because we live in an all-electrified world these days. These radio waves can cause an electronic device to malfunction, to fail, to just not perform like we want it to perform. I know the biggest tragedy that ever happens in my house is when the internet goes out for any reason. That can be caused by electromagnetic interference, and that's why it's important. EMI shielding is everywhere. Coaxial cable has EMI shielding built into it. Your cell phone has EMI shielding built into it. Your computer, your car, aircraft, EMI shielding is everywhere around us. Most of the time, EMI shielding is made of metal because metal is very conductive and creates a barrier to the radio waves passing through to the part of the electronic device that we want to protect. Now, metal is not the only EMI shielding material, but it's far and away the most common. We can't use, for example, rubber or plastic in their native form because they're not conductive. They're completely invisible to the radio wave. But if we infuse plastic or rubber with a conductive filler, say carbon black, we can create a hybrid EMI material. That's great, but we have to be very careful. If we add too much carbon black, too much conductive filler, we degrade the plastic or the rubber and it doesn't function or last very long. Conversely, if we don't add enough carbon black or conductive filler, then we don't get any EMI shielding. Now, the problem with metals and polymers and conductive fillers is that they tend to be heavy or dense. They don't always conform well to three-dimensional material, three-dimensional objects, and they tend to be thick. So these are the sorts of things that designers are trying to work around to get the thinnest, lightest material possible to serve as the EMI shield. I've already given you a few general examples of EMI shielding that you're already in contact with on a daily basis, but I'm going to go into that topic in a little more detail. There are various types of EMI interference. There's natural EMI, and then there's man-made EMI. EMI can be measured by how long it lasts, and it can be measured by how much impact it has on the performance of the electronic equipment in question. How much of the signal gets degraded, how much of the circuit gets degraded. EMI is in every consumer electronics product. So in our Alexa-driven world, you have to think about a refrigerator, washing machine, anything that the Internet of Things might touch. EMI can cause it to fail. Think about transportation. Autonomous vehicles will be entirely dependent on great EMI shielding. Electric vehicles require great EMI shielding. And perhaps most importantly, mass transportation. The aircraft industry relies heavily on EMI shielding, but so does every form of mass transportation, including buses and subways and trains. Healthcare is a great example of where EMI shielding is very important. We have all sorts of medical devices, implants, that if not for EMI shielding, they could cause a catastrophic failure. A great example is a pacemaker. You've probably been in a hospital and seen a sign where people are warned about pacemakers not to go near certain testing areas in the hospital. The pacemakers are now lined with EMI shielding, so they're less prone to that sort of event. So EMI is all around us, but there's one burning question. If metal and plastics and rubber and conductive fillers aren't good enough, what is? Graphene, and that's what we're going to talk about next. Graphene is virtually weightless at 0.77 milligrams. It's very, very flexible like silk, and it's ultra thin. The material that we're talking about for EMI shielding will probably be measured in the nanometer scale. Less than a micron, but more than a single sheet of graphene. It's a multi-layer application. As long as we can make the graphene conductive enough, it will function as a good EMI shield. What's conductive enough? Well, we have made the graphene have a sheet resistance as low as 0.5 ohms per square, and that has produced an EMI shielding effectiveness at 1 gigahertz of 90 decibels. The EMI shielding effectiveness you get from graphene will be a function of how thick you want the graphene to be. But remember, thick and graphene are relative concepts. We can fold over a thin sheet of graphene to double its thickness, and it will still be measured in nanometers. What we've got is a material that's ultra thin, virtually weightless, and provides the same EMI shielding effectiveness as metal. It's the state of the art. It's not the future. It's here today. And if you want to know more, give us a call.